Good afternoon, everyone. I would like to extend a warm welcome to each and every one of you who have come to the workshop today, which marks the closing ceremony of the Regional 2022 ITU AIML Challenge. Professor Brijesh Lal and Dr. Arzad Alam Khairani have been the professors in charge of this activity. Coming to the next slide, this is the agenda for the workshop today. I would like to request Ms. Vinti Nair, who is the project manager and consultant at IIT Delhi, to please walk us through the various activities that had been undertaken in this Build-a-thon. Over to you, ma'am.
Thank you, Dr. Timmy. Alok, can we have the next slide, please? Thank you. About the challenge, this challenge has almost been a 4-month-long activity. And I'm very glad to see so many students sitting in the IIT Delhi building over here. We have it going on in person also, and there are, of course, participants online. And it basically provides a platform for students. A lot of students from all disciplines are working on AIML to solve a lot of real-life issues. So it provides a platform for the students and professionals to participate in global pre-standard activities, because this is aligned to the ITU global challenge. So whatever is happening here will now, the winners will go into the ITU global challenge. So, and it explores problem statements in low latency closed loop control with applications in 5G. Professor Arzad is worked on the edge with Professor Lal and his team. And so this particular problem statements are going to be actually ultimately implemented on the testbed, which is in IIT Delhi. It's a 4-month-long activity, as I said, and went on in phases. We had a number of public events, even a landing page, a website was created by Gaurav over here. And we had one expert talk conference right in the beginning, 2 roundtables, and the closing workshop, which is today. The registered team have received support from mentors within IIT Delhi. And we are so happy to say that we do have a good number of registrants who actually gave their submissions for the problem statements and now, of course, evaluated. And webinars and workshops were conducted. We also had a number of experts coming in from abroad. We had them coming from IIT Madras. And winning team to get free study to EU and entry to the global round. And the final contribution will be the contribution to standards. So we're going to work with the ITU consultant, Vishnu, and work on a number of documents which we're going to submit. So now I hand it over to Professor Arzad, who's been in charge of this whole challenge. Thank you.
Hey, good afternoon, India time, and good whatever time is there where you are from right now. How do we even? Alok, can you please share my slides? This is Arzad. Okay, thanks, Alok. So this is a work that we have done as part of our activities in edge-based intelligence and applying that setup to support bilateral teleoperations of robots. So brief history is that we were part of 5G testbed activity. We designed HC compliant MEC system, integrated it with the 5G testbed, and then we brought in this application of bilateral teleoperations of robots. So today we will share our findings so far. This is an activity which is currently going on. Lots of activities are going on here. We are going to just discuss few aspects that we have been able to understand from this setup. So today, while I'm presenting the same slides here, this is also being presented at AIML conference in Bangalore, which is going on currently with Munib. So Munib will talk about the evaluation part today. Next slide, please. So the outline is, I discuss about the background and motivation, some amount of setup detail, then signal characterization. So what exactly is meant by signal characterization will be clear when we come to that slide. Events of interest in detection and future scope. Next slide, please. So when we are when there's a robotic interaction involved, there can be multiple ways. One, a very simplistic view is assume that there's an autonomous, completely binary, autonomous and an assisted setup. So when we have bilateral teleoperations, humans exist in scenario as a controller. So there's a human which is controlling. You can see on the left side of screen, your left side of the screen, which is getting the sense data. So the controlled object is on the right side of the screen from your point of view. So the controlled robot is on the right side, that is sending the information. So there is the sensing part that you see there. The human in loop is getting this information continuously and applying some control. So the arrow coming out of the right hand side robot is the sense data. The arrow going into the right hand side robot is the control that the human is applying, right? Next slide, please. So if we apply this setup and if we assume that the communication pipe between the controlled robot and the controller is provided by 5G. So we'll just assume for now that this communication pipe is provided by 5G network. Then we end up in this kind of scenario where we have this 5G part in between. I don't, my screen will be visible. No, right? Okay, let's see. Okay, let's see. So there's this remote control data going into the robot. The sensed data is coming into the cloud server, right, where the human operator is. Next slide, please. Now, there are some challenges with this kind of setup. One of the challenges is that typically, so here when you see the top left image, it is basically a doctor controlling a telesurgery equipment, right? So this kind of setups usually rely on what is called move and wait approach, where you do not take, so if you have to take a bigger macro action, you divide it into micro actions, small steps. You don't take the complete action in one go because something may go wrong in that sequence, right? So you divide it into a sequence of small steps. So that's what we are calling it a move and wait step. So there are different steps for that particular action. Let us say that you have to pick up an object, right? So that object, the act of picking up an object will be divided into multiple small components, right? So it's like a movie running in a slow motion kind of for now. And there are n of I number of such steps involved in that activity, end-to-end activity. Each of this step, micro step, will consume some time. Okay. Now that is where the problem comes in. The controller is sitting far away, and I'll give you the delay computations in a bit, depending on the distance between two devices. For now, just take it on face value that this time, TR and TD, which are the round trip delay, the delay in the data coming from robot to the controller and going back, the control going back to the robot, that can be very high if we are talking about distances of order of even 300 kilometers or 400 kilometers, okay, which is not a big thing in India. So the north to south is roughly around 3,500 in India. So we'll be having significant delays. Okay? And that gets multiplied, that is that comes in each and every step. Okay? So kind of accumulates, the complete delay accumulates. Next slide, please. So this is a picture which will possibly convey the idea better. So you take one step. So this is one step, just starting. It takes some time to reach the receiver. And then there is an acknowledgement back, right? So each step is basically a micro step will also consist of multiple control signals, right? So that all the control signals are here, one after the other, they are being transmitted. Each of them suffer some delay. So TP, some distance divided by the velocity of the light. And the last acknowledgement comes to the transmitter after some time, right? So this is a breakup of all the delay that I discussed in the previous slide. Next slide, please. Okay. So because of these delays, now you can see the second challenge that we will face. For example, so just take an example of a scissor falling, right? So you are trying to pick a scissor and it just falls. So from the grasp of the robot, how will the end user or the controller get to know about it quickly, and also should be in a position to avoid such slip, right? But our problem here is that the delays, the feedback to the controller to take preventive action will be futile in this case, and the round trip time for the to be able to is prohibitively large to be able to get any corrective measure in time. Next slide, please. So people will say that 5G comes with something called ultra reliable low latency communication. So when they say low latency communication, it essentially means end-to-end delay of less than 1 millisecond or 2 milliseconds. Okay. So someone can say that 5G already provides ultra reliable low latency communication. So here's a standard diagram, triangle of 5G standards, what it promises. On the top, it promises something called enhanced mobile broadband, which means high data rate. That is what you have been used to in case of 4G. Right? On the bottom right side, it provides something called ultra reliable low latency communication. So low latency communication itself, because in our case, the data requirement is huge. Low latency communication assumes in some sense less volume of data. So our use case is sitting somewhere in between, haptics based robot. So we think that vanilla URLLC paradigm will not be sufficient to address our problem. Next slide, please. Now, 3GPP is a standardization body which has standardized 5G activity, the complete 5G specs. And our MEC solution, the edge computing solution, was based on another standard, which was coming from another standardization body called ETSI. There's a lot of, so ETSI started early on around 2013-14 timeframe, and they were able to give out the MEC spec quickly, and we adapted that. 3GPP started this activity slightly late, around 2020, but they are also now getting into this kind of split control of AI/ML operations and model distribution. So you will be having many edge devices which will be collaborating among each other and share their information. So that's called federated learning also, right? So distributed and federated learning paradigm comes in naturally in this case. Next slide, please. So if we kind of marry the split control paradigm with the edge, with this 5G communication, with the haptics based system, right? So if we merge all these three, we end up in this kind of scenario where you have a robot controlled by a human controller on your right side. There's a 5G network with an addition that there's an edge device which is sitting very close to the robot, right? So physical proximity is there. So physical proximity would, in our case, imply low latency. Okay. Next slide, please. Okay. So now we will come to how these systems, what are the use cases of these systems, right? So next slide, please. So there's a series of papers and also experimental results from practical deployment, where several hospitals in China came together and they performed telesurgery, on live telesurgery. Next slide, please. Next slide. Yeah. So this was roughly the topology that we are talking about. The control, the robot was actually here in some hospital in Yantai, which is controlled by a hospital surgeon who is sitting in Beijing. Okay? Even if I check the over the air distance, direct line of sight distance between these two sites, we are talking about more than 500. So this was 512 kilometers just over the air, right? Now, assume that you have a fiber optic network coming in from inland or maybe over the sea, and you have multiple repeaters and other devices in between. Then we are effectively talking about a very large delay. At 512 kilometers, you can check, you can do a basic calculation going back to our class 11, 12 math. How much will be the round trip time if we are looking at this 500 kilometer, right? You can also think about how much time it takes for some object to slip. If you are just holding some object and the time that it takes to slip is very small, it's less than 60, around 60, 70 milliseconds. It's not in order of seconds, right? So when you do all this math, you will see that the distance in this case is huge to avoid this kind of events. Next slide, please. So here is an example of from within India. So we were trying to understand what will be the overall delay, round trip delay. This does not depend on the speed, by the way. So this just depends on the distance, physical distances, and congestion in the network. So the closest we could see was Delhi to Indore. Round trip latency, this is publicly available statistics, was around 30 milliseconds, 38 or 40 milliseconds. That is a average, right? Worst case could be of order of max was of 43 or 44 milliseconds. So we are talking about this kind of round trip delays for each and every packet that is being sent. Each control, each sense data sent, and each control coming into the hospital. Okay. Next slide, please. So it does make sense to have, if you want to avoid some kind of unwanted event, it does make sense to have an edge device which is just next to the robot where actual activity is happening. Okay. I hope this motivation is clear. If there's any question, you can stop me and ask. Okay, next slide, please. Now, there's another complication that for such, so I just, in the previous examples, I just said that there's a sense data, right? The sense data itself can be of multiple types. So we call that multimodal data. So there are multiple modes in that data stream. Depending on what you are actually, what data you are actually streaming from one end to the other, their requirements will be different. Okay? So for example, some may have a relatively low data rate, but very stringent. So this is a high data rate, very stringent latency requirement, and all kinds of mix are possible. Low data, high stringent latency requirement, and so on. Right? So this complicates our problem. Next slide, please. So this kind of setup was not available in ETSI MEC solution, and while we are currently standardizing the edge app, the corresponding edge app solution or architecture in 3GPP, this part, the multimodal part, is being taken care of now, and we are able to segregate or represent one application as consisting of multiple services. This kind of functionality was not completely there in case of ETSI architecture. So we will be also extending our testbed here to be in line with the 3GPP architecture, which is being frozen now. It's not frozen, so release 18 is going on. We are closely monitoring that. So we think that if we are able to put some intelligence close to the controlled device or the robot, and this intelligence is what was the objective of this particular build-a-thon. So we gave two problem statements, PS1 and PS2, as far as I remember. And now you will be able to relate those problem statements with the scenario that we are talking about possibly. Most important part was this quick takeover. So we want that the edge, the intelligence running at the edge should be able to quickly take over the control of the end robot. Next slide, please. So this is the setup that we have here, and most of the data that we collected was from this setup. we are not performing any human surgery here right now. This is a very simple, this is a very baby step towards that end objective, right? So we have a haptic glove on the right hand side, which sends the control signal. So this is called the forward channel. It sends control signals to Allegro robotic hand, which is given on the left hand side. One of the problems when we go to the field, one of the problems is that you can have different hospitals will have different kinds of products here, right? So they need to understand each other's language first of all. So you need to have those kind of translation layers in place. For example, this Allegro hand is 16 degree of freedom, and the haptic glove is just 11 degree of freedom. Okay, so when you do some movement in the robot in this haptic glove, how do you translate that into this 16 degree of freedom Allegro hand language, right? So, and the reverse. So that has to be done, which has been achieved. Next slide, please. And the backward channel is the haptic signal which goes from the Allegro hand into the haptic glove. So all these fingertips will have a force sensor, and that pneumatic data will go into the robotic hand here. So that's a sensed signal that we have been discussing so far. We are calling it haptic signal, but it's one of those modes in multimodal communication that we were discussing. Next slide, please. Okay. So overall, this is the setup. So these are all robotic devices. So we used robotic operating system, ROS. We worked with ROS 1 only. We have been told that ROS 2 will have better performance in terms of delay. We are trying to migrate to ROS 2, but we are not there yet. So we are currently working with ROS 1 setup only, robotic operating system. So we have this haptic glove on the left-hand side here. So we have just flipped the sides for now. That becomes one node in the robotic operating system domain. That publishes and subscribes. So robotic operating system works on hub-sub model. Hub-sub model is basically where each entity, so there is a central broker, and each entity which is interested in communicating with others, they publish. Someone which wants to send data, they publish their topics. Right? So this is a topic, let us say feedback signal or the force signal. And the devices which are in the other nodes in the same system, there can be multiple robots connected to the same central broker, right? So others who are interested in getting that data will subscribe to that particular topic, right? So there's a notion of topic. Topics are published or they are subscribed. Okay, so haptic glove will be publishing its control topic. The Allegro hardware is going to publish its own force data, okay, and its location data, the joint location and so on. So, and this is going to subscribe to the topic which is published by the haptic glove. Haptic glove is going to subscribe to the topics published by the Allegro hand. So this is how the complete communication happens. So now we inserted this fourth layer. So we started with pure robotic communication. We brought in 5G, then we brought in Edge. Now we have brought in ROS as well into this. Next slide, please. So this setup has been integrated with our 5G MEC system. Currently, it is not 3GPP compliant completely. It is purely ETSI compliant. This is just an indication of that. Next slide, please. Okay. So having achieved this setup, the following is what we have done so far. There are a few other things which are going on in parallel right now. They are not complete. So we'll hopefully share it at a later occasion. So first of all, we thought that there's some possibility of data compressibility. Okay? We don't need to possibly send all the data in raw format as they are generated. So that is what happens in your video transmissions also, right? So you get a frame, the complete video is not sent as is because that takes huge amount of bandwidth. We compress at the source and decompress at the receiver. So the same kind of feasibility is what we try to understand. Next slide, please. And the second part that we did was to understand agifiability of an intelligent algorithm. Okay. So one can come up with an AI ML algorithm which runs at the edge to avoid some event, let us say, or to detect some event and apply timely corrections. Whether that algorithm will actually work or not, right, for that particular application. So that is what we mean by edgifiability. I'll come to details of this in 3 or 4 slides from now. Next slide, please. Okay, next slide. We can go to the next slide. Okay, so this is signal characterization. So what we did was, this is your Allegro hand. Okay, it has 3 fingers and 1 thumb. So we were just playing rock paper scissors with this. Okay, so that's what we did. And because what will happen is, in typical applications, one robot will be basically asked to perform same kind of task again and again and again, right? So there's some amount of repetitiveness in this setup. So we thought, let us go with extreme. So this is paper and this is rock, right? So, and this is Caesar. So this has enough movement. So like complete variation from all the fingers open to all the fingers closed and some in between. So that's what we tried to do. And that's what you can possibly see. So we were just cycling through this pose randomly over time and try to see what is the level of compression that we can achieve. And so next slide, please. So you have heard of something called entropy already in information theory. Most of you have possibly heard of entropy. Entropy helps us understand what is the number of bits required to represent some information, right? So we characterize that entropy. Only problem here was that this is a stochastic process. So we have to look at some dynamical model. So we modeled this system as a Markov chain, and there's some equation for getting entropy, right? Some transition probability matrix and so on. One important thing that we did was we changed the sampling interval. So sometimes we were sampling very quickly, sometimes we were sampling very slow. So we wanted to understand what is the result of, because sampling directly relates to the data that is generated from this robot, from this Allegro hand. Okay. So we wanted to also understand what is the control or sample rate that we can provide. Next slide, please. So it turned out that if you increase entropy, if you increase the sampling rate, average entropy increases not necessarily linearly. So it remains at very low value for quite some time, and then it starts increasing, right? So this knees, so typically in such systems, knees are the right places to operate. So that's one takeaway from this characterization. Next slide, please. Similarly, we were able to characterize the average data rate required to transmit this information. You can see that as sampling rate increases, just because entropy increases at this point, you need to transmit more data. Okay. So next slide, please. So here's some detail of this joint entropy. So there are different joints finger. So the way to read this is, in the index finger, there are 4 joints, 0, 1, 2, 3, right? So what is the entropy rate of the data just coming in from that joint, independently of everything else? That's what this right side gives, and this is at a particular sampling rate, 333 Hertz. Okay. We are not talking about joint entropy right now here. So next slide, please. Okay. So we can also have, when depending on the movement of all these serial chains which form the individual robotic hand fingers, that there is some amount of correlation in the data that they are generating. And if we are able to quantify that data, we will be able to achieve some amount of compression. So we could see, for example, when there is a very less correlation metric, right? That means we don't even need to bother about that part. So next slide on this, please. Okay. So we were able to characterize entropy. We have some trade-off between the sampling rate and the data generation and the corresponding entropy rate and so on. So it looks promising that without losing a lot of data, we will be able to convey most of the information. That's the kind of takeaway from that experiment. Second part is this edgifiability work. And we wanted to understand that can we apply any AI ML algorithm blindly to this system and will it work? Or is there a variance, is there some relationship between all in terms of feasibility, the AI ML algorithm, the task that you are actually wanting to execute, and the communication system? So the delay required, the delay guaranteed by the communication system, right? So that's our edgifiability. So edge part here comes from the fact that we are using a particular communication system which is having an edge in it. So we started with a slip detection algorithm or a slip detection system where there's a controlled slip. So I'll give more detail about this. The robotic hand picks an object. So that is what we are calling grasping. Grasps an object and then lifts it and then moves and then just remains stationary and let the gravitational force control the movement of the object, and it slips after some time. Okay. Next slide, please. Previous slide, I think. Yeah. So this is the overall setup. So we are reaching to the object, grasping the object, and then lifting the object. This is done in simulation to ensure that there is repeatability across different experiments. Okay. Next slide, please. So if you do signal analysis, this is a signal coming from that the 4 signals in each tip of index finger. So this is just the tip of index finger. We are looking at all the 4 signals coming from all the different tips. Okay. So you can easily characterize the reaching part, the grasping part, the picking part, and the onset of slip. So this is the point where slip actually happens. The object actually slips. So, and also there's if we apply some kind of transformation to, so turns out that this is not a sufficient statistics. We can have a kind of a Laplacian. We can apply a Laplacian transformation to the information that we are getting here, and we get a better characterization. So the lower part is just a transform version of the upper figure, but they are conveying similar kind of information, that the actual onset of slip can be detected here based on if you analyze the Laplacian, and actual slip happens at this point. Next slide. Okay, so what we did was that we were getting this time series data. So we applied Laplacian to it, and then there was a very simple logistic regression algorithm. So our objective right now in this activity is not to come up with a very good, very super optimized kind of algorithm to detect the onset of a slip, but just to see what is the effect in terms of latency of running this kind of algorithms. Okay. So we just chose one logistic regression algorithm here. There can be much more. You can do lots of optimization here, and this gives a prediction, that a running prediction whether the object is about to slip or not. Next slide, please. So this is the basic motivation behind, or the idea behind this edgifiability notion. Okay. So what we did was, please pay attention to this part. So assume that this is the first time instant where this event can be detected. That event in our case right now is a slip, right? So this is the first time where the event can be detected. So a delay in detection is performance of your algorithm, right? So if you are running any algorithm, and that it can be characterized using the delay, the time it took to detect the onset beyond this first instant where it could have been detected ideally. So this is where the event got detected, let us say. Then if your event is detected, you have to apply some corrective measure. Before applying that corrective measure, you have to compute, you have to find out what that corrective measure should be, right? So this part, this PO part, is that delay that you detected, you found out that there's onset of some event, and now you have to apply corrective measure. What are the parameters of that corrective measure is decided at this point. Okay, so that's about the traditional control that you would be doing. Now, if you are not doing this kind of closed loop control, right, where you are not continuously detecting and applying this kind of algorithm, then that is what I call open loop. The event would have occurred at this point. If I had not applied any such control, right, the event would in open loop, the slip would have happened at this point. Because we started applying this control early on, we get some more time, right? So that because of this time, we started applying control slowly. So we are actually getting some additional time of lambda here. This is what we are trying to understand. If lambda is large enough, that means your algorithm is good or your setup is edgifiable, right? Because you are actually getting more freedom in applying control. Is that part clear? Any question on that? Okay, next slide, please. So here is a result. Here are the results from our slip detection. So as I told you already, our algorithm was very trivial, plain logistic regression. You can have other algorithm also here. What we did was just increase the gravitational force in that simulator. Okay, what that would mean is the open loop time for the event would reduce as the gravitational force increases, right? So onset would be possibly at some time. So you got an onset of an event at some time, and the exact time at which the slip would happen will start reducing if we increase the gravitational force, right? That's quite natural. So that is what we did. We increased the gravitational force and we found that this lambda, so this is actually lambda, is we are getting significant improvement or 3 seconds additional till 1.5 till 1 second additional when we are applying this control. Okay, whenever the gravitational force is within some limit. Beyond some point, we are not getting any significant benefit. So we are as bad as open loop control. So this says a lot about your algorithm as well. So whatever algorithm you run at the edge, it may or may not be good, okay, depending on this amount of time that it provides you. Okay. Okay. So next slide, please. So we were able to get this additional 2 to 3 milliseconds. I think 2 to 3 seconds in the. So this is just the delay, but we are able to get 2 to 3 seconds in terms of being able to control. So our definition of edgifiability is it's an intuition. We are still not giving a very formal definition here. It essentially means that there is an existence of a non-empty set of physical properties when the control algorithm is indeed successful. So that's our objective, right? So we are running an algorithm at the edge, which is detecting and controlling. It is successful in achieving the objective. So that's what we mean by edgifiability. So edgifiability is for any algorithm as such. Next slide, please. This I will skip. So I think I have covered both the topics. So we can go to the last slide. Yeah, this is where I will stop. Yeah, we are running some more work. We are doing some more work here, estimating the geometry of shape and latency aware algorithms. That is the objective of this particular build-a-thon. Thank you.
Thank you so much, Professor Arzad, for this informative talk. Shalo, could you please switch to the other set of slides? Thank you so much. Please switch the slides, move to slide number 5. Next slide. So I would like to welcome Dr. Vineet Gokhale, our second expert, who will be giving us more details on tactile internet and its communication aspects. Dr. Gokhale is currently pursuing his postdoctoral research at Delft University, Netherlands, and has some significant research experience in the area of robotics and automation. Over to you, Dr. Gokhale.
Hi, good afternoon, everyone. Am I audible?
Yes, sir, we can hear you.
Excellent. Thank you. Thank you so much for the invitation and kind introduction. I would now like to share my screen so that my slides are visible to everyone. All right, does this work?
Yes, sir.
Excellent. Thank you so much. Right. The topic of my presentation would be tactile internet. I'm aware that this build-a-thon has been focusing on detecting slip detect on activities like slip detection and a few more things with a very sophisticated setup that is built at IIT Delhi. What I would like to focus on is tactile internet, which deals with a transmission of kinematic and haptic feedback or tactile feedback in general over a network. And this is to facilitate teleoperation in remote environments to do very specific tasks there. So I'll touch upon this subject and also give a brief overview of what we here at TU Delft have been involved in, specifically with respect to tactile internet communications. All right. So as a human civilization, we have come really far with respect to how we have solved a variety of problems that we have been facing, right? But still, we are confronted with several challenges that still lay open out there. And that also brings a lot of value to the science we do, right? To be specific, several disasters, right? Whether it is natural or man-made. So we have been seeing more of them in the recent years. So what do we do in case of such disasters? There are a vast amount of lives lost, and also several rescue personnels are put in harm's way when they are involved in rescuing innocent lives. So how do we, first of all, facilitate quick rescue? Second, do this without really involving loss of lives of rescue personnels. Telemedicine, right? By telemedicine, I don't mean just monitoring and a diagnosis of diseases remotely, but also operations, right? Telesurgery. We know that many parts of the world still don't have proper access to healthcare. And if we could somehow make healthcare globally accessible to everyone, especially in the era where the amount of doctors out there with very specialized skills, such number is really low, and the demand for them is growing like anything. COVID especially has completely redefined the way in which we socialize with people. So there is now less and less of networking in physical world and more networking online, right? And one aspect of this is online meetings are still not as effective as meeting someone face to face, because a physical interaction involves a lot of gestures that are touch based, right? Like handshake, like a pat. The internet infrastructure is still not up, or still not ready for giving or rendering such handshakes and hugs to be available online. And finally, how do we enable physically abled people to have better quality of life? So these are all very important problems and also challenges that pretty much everyone faces in day-to-day activities. So now the question is there a way to handle these problems in a better way? Fortunately, the answer is yes, and that is through what is called as tactile internet. So tactile internet is an upcoming technology which facilitates transfer of skills over a network or to remote places. So let's look at the working of tactile internet through a video demonstration. So here in this video, you see Jeff Bezos trying to teleoperate a robotic arm that is physically there. So Jeff is wearing an exoskeleton which captures his own motion signals, and those are then transferred to the tactile robot that you can see, because of which the robot is able to very accurately mimic his own hand motions. And whenever there is a physical contact with the robot hand and physical objects, right? Forces are generated very similar to how we interact with objects in real world. And the beauty of this robot arm is that such forces that are generated remotely are picked up by the robot arm and transferred back to Jeff, who is the human operator in this case. And the exoskeleton also has the necessary capabilities to display the force feedback to him. So in essence, what's happening is Jeff is able to get a feeling of actually holding or even lifting the objects that the remote robot is actually doing in reality. So what that means is Jeff is now able to transfer his skills to the remote robot while also getting a feeling of actually being in the remote environment. And this skill transfer or transfer of skills enables him to do very high precision tasks that are otherwise impossible to do in remote environment. So that's the essence of tactile internet. Now, this interaction in this particular demonstration is happening without a network, in the sense that the exoskeleton that he's wearing and the robotic arm are connected to the same computer. But it's not hard to imagine a network, a telecommunication network sitting in between these two. So this is tactile internet essentially, right? So when it comes to interacting with someone or something over a network, we are already extremely accustomed to audio video type of interactions. You speak to people that are located elsewhere. You can also see them, right? Audio video communication is something that we have pretty much conquered. And touch is now the next barrier. So tactile internet precisely facilitates this. Okay, now, what is something that touch feedback gives us, which existing audio video communications don't? And the answer is pretty simple, right? Force feedback or touch feedback. But why is touch feedback important is the primary question here. And I would like to answer that through this video. So here you see a person trying to light a matchstick, and he just does that in a flash, right? He holds this matchbox, takes a stick out of it, and using just one hand, he's able to light it. So that's how simple the task is, right? That's no big deal. However, we still don't quite understand what is the role of touch and or how important touch feedback is in this particular application, right? But now let's try to reflect on that a bit. So here is another video where a subject's hand is anesthetized, which means she does not feel, she does not get a sensation of touch anymore. And now this subject tries to do the same activity of lighting a matchstick. And as you can see, the absence of touch feedback makes such a huge difference, in a negative way, of course, in the same activity, right? So the subject here struggles and struggles and struggles even to hold the matchstick, right? And finally, she's somehow able to get there, but not in the most convincing fashion. So this should pretty much give a sense of what it means to teleoperate something or control something in the remote environment without the feeling of actually touching the remote objects. So now that we know the importance of touch, we know what things can tactile internet enable. So essentially, it lets us do things in the remote environment with precision and with speed, as in the same amount of precision and same amount of speed as in a conventional setup. By conventional setup, I mean both the operator actually dealing with physical objects in local environment. Now over to the applications of tactile internet. I'm pretty sure a lot of you already have very creative ideas on how this technology can be put to use. But there are some already identified use cases which will benefit tremendously from tactile internet. Like I mentioned earlier, telemedicine, right? Whether it is monitoring or diagnostics or even surgeries. So several big players in the telemedicine industry are already closely looking and even working on using tactile internet in their use cases. Then we also have a plethora of other use cases of tactile internet. Industrial automation, right? So you have this factory setup with extremely unfriendly conditions for human habitation, right? It need not essentially be a factory. I'm taking factory only as an example, but it could be a coal mine, right? Where the temperature and pressures are just not good enough for humans to actually work there. So one could deploy remote robots out there that are going to be manually controlled by human operators that are located in a much friendlier place. Tele-repair, right? For example, we have heard of satellites breaking down, or even several modules of International Space Station breaking down. So what happens every time is whenever this happens, astronauts are sent from ground station all the way to ISS, where they have to perform risky spacewalks and fix the module and come back, right? This is a very, very expensive business. So instead, we could have a permanently deployed robotic arm, a dexterous and an agile robotic arm out there in International Space Station. And whenever something breaks down, you could simply control that robotic arm from ground station and do the necessary repair without even having to shoot someone all the way to the International Space Station. So a lot of industries who are now very active in space will benefit tremendously out of this. E-commerce. So whenever we buy some article, right? So we are interested in the shape of it and also how it feels physically, right? Whether it's the texture of it, hardness, softness, the weight. Now, when you do online shopping, such exploration is simply impossible because we don't have a means to feel the texture of it or even sense the texture of it. So such e-commerce platforms will definitely benefit from tactile internet because now the users or consumers can make informed decision on how the object of interest feels before even going for it. Gaming, right? One can augment tactile feedback with virtual reality to make video games even more immersive. And finally, training. So let's say you have a live surgery going on, and there is an expert surgeon who is performing these operations. And there are several trainees out there who not just want to see the actual operation, but also want to feel the micro movements that this surgeon performs, right? So what one could do is capture position and velocity signals of surgeons' hands and feed it to these trainee surgeons so that they are aware of the kind of dexterous or micro precision movements that go into performing a surgery. All right, so in a nutshell, tactile internet is here to revolutionize each and every aspect of human lives. And to go forward, let us pick a very specific use case of industrial automation or semi-automation, if you will. And let's dig a bit deeper into this to get a hang of what exactly are we doing here at TU Delft in terms of advancing the tactile internet technology. Right. So here is a typical industrial semi-automation setup. And the control domain is the actual industrial plant, where there are several independent robotic arms that are to be controlled by human operators located elsewhere, right? And this is usually called the master domain. And the industrial plant where you do the actual activity, physical activity, is called the control domain. And there is a network domain which is responsible for a communication between master and the control domain. And let's assume there are these different tactile robots in the control domain. They're all mobile robots, and it makes sense to leverage wireless communication for this, right? So let's say that all of these robot arms are served by a Wi-Fi access point, right? So which means if there are multiple robots being controlled simultaneously, so there is a constant exchange of signals between the master domain and the control domain. And the signal from master domain goes all the way through the network domain to the Wi-Fi 7 access point and is finally delivered to these stations, right? And on the feedback path, you have these robot arms share the wireless channel that's out there, and then get access to the Wi-Fi access point and send the signals back to the master domain, so that the human operators can both see what's happening in the control domain as well as feel what's happening in the control domain. To be more specific about what is being exchanged between these domains, so as you saw earlier, the human operator wears an exoskeleton. So the kinematic signals captured from this exoskeleton are sent over to the control domain. And these kinematic signals usually are comprised of position signals, position of the hand, of the finger, and also velocity, right? At what speeds are these individual entities moving? And this kinematic signal facilitates the robotic arm in the control domain to mimic the user movements as precisely as possible. And on the feedback path, you have the haptic feedback that the force sensors or the robot or the haptic sensors on the robotic arm are capturing, as well as the master cannot do any activity without seeing what's happening on the other end. So we also have a vision camera on the robotic arm that sends back the video feedback to the operator, right? So essentially, on the path from AP to station, we have kinematic signals that are going this way, all the way to the stations or the robotic arms. And from the station to the access point, we have haptic and video signals going through the network domain all the way to the master domain. Now, let's closely look at what's happening in the control domain, right? As per this schematic diagram, it seems like the human operators in the master domain can be located in different networks, whereas the control domain is just the industrial plant, right? Where a lot of coexisting tactile internet streams are being communicated. So we'll focus only on the control domain for this talk. And as I already spoke about, we have both haptic feedback as well as video feedback being generated in the control domain, communicated to the access point, right? So these are two very different type of signals involved that are to be sent to the master domain. So how are they different? They're different both in terms of their characteristics as well as their quality of service requirements. For example, if you look at this table, right? So we have kinematic and haptic signals, which require extremely low latency in the order of sub 5 milliseconds in order for the human operator to get a very realistic feeling of teleoperating in the control domain. And such an ultra low latency application, right, is something that was unforeseen. We are used to audio video communications, and such communications are extremely forgiving in terms of their latency requirements. If you look at this, video communication will go smoothly, even if the latency is as high as 40 milliseconds, right? On the contrary, the latency requirement of haptic or kinematic signals are an order of magnitude lower, right? This is already extremely challenging to achieve with the existing internet infrastructure. Coming to reliability, the haptic or kinematic streams are a little more forgiving in terms of reliability than video streams. So typically, it is known that about 90% reliability is okay for these streams. On the contrary, video requires extremely high reliability, which is about 98%. The kinematic and haptic frame sizes are very small, right? Because all we are transmitting is position, velocity, or force signals. And you can pretty much assume every frame that is generated is about 100 bytes. And such frames come really, really often, which is about 1,000 per second. On the contrary, each video frame is super heavy, about 25,000 bytes long, and they come relatively less often, about 60 hertz, right? So as you can see, there is extreme heterogeneity involved in the way haptic and video feedback manifest themselves, which means these two streams have to be handled very, very differently in order to comply with their respective quality of service requirements. We'll now look at what happens in state of the art. By state of the art, I mean a very recent work in tactile internet that deals with how to schedule these haptic and video transmissions. So we have a robotic arm, and there are haptic sensors and camera, each independently generating their own streams, which is then packetized and sent over a Wi-Fi channel. Right, and typically this Wi-Fi channel is extremely prone to latency and losses, and that's because we are talking about a Wi-Fi channel that is being simultaneously utilized by several devices, right? So if you look at this, each robot arm is looking for access to the Wi-Fi channel for transmitting haptic and video frames. And the access point itself is looking for access to the wireless channel for transmitting kinematic frames, right? So which means there is extreme contention or in some sense race happening between these devices to transmit the data that they are generating. And what happens? The problem now here is the state-of-the-art method packetizes haptics samples as well as video samples together. And as you can see, it is being enqueued in the same queue and being dished out whenever the device gets access to the wireless channel. And this is extremely problematic given the heterogeneous nature of these two streams. We'll look at this in a bit more detail. So what happens in state of the art is, let's say you have a video frame being generated. This is where it's being generated and transmitted. And let's say this is the receiver, and this is the wireless channel with about 10 Mbps of channel data rate, right? And at a time equal to 0, we have a ginormous video frame that is generated, and that needs to be sent over this channel to the receiver. And if we do it in just one shot, because these video frames are extremely large, they take a massive amount of air time to be delivered to the other to the receiver, right? So just as a ballpark figure, let's say this video frame takes about 32 milliseconds to be received, right? So which means the Wi-Fi channel is fully occupied for these 32 milliseconds during which a video frame is transmitted. And there are frequent episodes of these video frames that are generated per robotic arm here, right? And since there are several robotic arms, we can expect that there are going to be very, very frequent video transmissions. And if we see such a massive latencies so often, then the haptic frames are going to suffer, right? For example, H1 here, which is a haptic frame, which was generated right after the video frame V1, it gets delivered only at 33 milliseconds. That's about 30 milliseconds of latency already, just because there was a preceding video frame. H1 just got unlucky, right? So how do we handle this? This is a significant problem because we are looking at latencies of 1 to 5 milliseconds, right? So it's very probable that the haptic frames will find the wireless channel super, super busy. And such a scheme is just not going to work, right? So what the state-of-the-art method, which is called the visual haptic multiplexer, does to address this problem is that it chops the video frame into several small fragments, right? The primary issue here was the video frames are huge, and each frame was sent in just one shot. So this can be solved by a very simple technique, that's to split these video frames into multiple fragments. And like I told you already, there is a video frame being generated, and there is also simultaneous haptic frames being generated, right? So what VHMux, which is short for visual haptic multiplexer, does is it augments a video fragment with a haptic frame that is generated. And every time the Wi-Fi device or the robotic arm gets access to the Wi-Fi channel, it dispatches just one such augmented frame. This makes sure that the subsequent frames that are generated don't face long delays because of this huge video frame. And at the same time, this also ensures that while you're transmitting haptic frames, you also have network resources made available for these video fragments. So you can keep both QoSs happy, right? Now, here is the problem with this. So let's say these devices, right? By devices, I mean the access point as well as these robotic arms, which I also call as stations. So there is a constant contention between these devices for the Wi-Fi channel access. And let's say if the station 0, which is one of the robotic arms, gets access to the channel successfully, right? So what happens then it simply sends out just one augmented haptic and video frame over the channel. And once it is done, it is just going to back off or chill out a bit until it has another haptic frame generated so that it can stitch this with another video fragment. All right. So while station 0 is done transmitting and happily relaxing, another station or another robotic arm wins the channel, let's say, right? And winning the channel is sort of a random process. I won't really get into the details of why there exists randomness, but you can pretty much assume that a device tries to access the channel whenever these counts hit 0, right? So station 1 hits 0 here, so it sends out an augmented frame. And whenever by the way, the access point is also constantly contending, right? Whenever the access point wins the channel, it transmits kinematic frames, right? Like we saw earlier, access point is going to supply kinematic frames to these devices. And let's say the access point is done transmitting kinematic frames. Access point is a very special type of Wi-Fi device, right? In the sense that it is in the race for channel contention. And when it wins, it also has a tendency to be nice to other people, right? So one a good way of thinking about this is there are several people in the race. All of these people are running independently. These people can be compared to stations, right? So they run independently. When they win, they transmit whatever they have. But access point is this nice guy over here who is also in the race, but he's also helping someone else to win the race, right? So what happens when access point wins is that it transmits its own data, and it also makes the channel available to other stations in a collision-free manner, which means as soon as the access point wins, it has kinematic frames transmitted, and there is also an opportunity for these stations to transmit their haptic and video augmented frame over the channel in a collision-free manner. In the interest of time, I'll skip further details on how this collision-free is guaranteed, but let's for now assume that that's how it works. Then these stations happily transmit their data in a collision-free manner. And once they have more data to be transmitted, they once again start contending for the channel. And here is a point where both access point as well as the station win channel or try to access the channel simultaneously, and there is a collision, right? The problem with visual haptic multiplexer is that here the collision happens between haptic video frames as well as kinematic frames. And these kinematic frames are usually large, or while the frames are small, they take a large amount of air time. And also, it collides with haptic and video frames. So this results in wasted bandwidth because you spend a lot of time in collision or waste a lot of time in collision. That also adds to the bad latency performance. And also, we saw the heterogeneity, heterogeneous characteristics between haptic and video frames, right? However, since you are augmenting both of them, they go into the same queue, and there is no provision of prioritizing haptic frame over video frame, right? If you want to send out haptic frame, you are eventually also sending out video frame inevitably. So there is no notion of prioritization here. So this such a challenge creates lots of opportunities for us to design algorithms that are tailored for tactile internet communications. And this is where we have our next work. So what we try to do is, this is the single queue stream, right, where payload is augmented haptic and video frames. And our proposal is that instead of augmenting them, send them to different queues. And haptic frame is sent over the highest priority queue because it has ultra low latency requirements. And video frame is sent over a lower priority queue because it has relatively relaxed latency constraints. Well, that's just a starting point. That does not solve everything, right? Because each of these queues are independently contending for the channel. And by making these queues independent, we are effectively increasing the amount of contentions, because now every station has two contending queues instead of just one, right? And also, since haptic frames are being sent over the highest priority queue, there is a possibility that the lower priority queue never gets access to the channel. In some sense, the video frames might get deprived. So these are the challenges involved, right? So we come up with, in order to address this, we come up with something that we called Vitals, that stands for Video Tactile Latency Scheduler. So Vitals tries to optimize scheduling between haptic and video frames at a device or at each device level, and tries to ensure that the quality of service requirements of both haptic and video frames are simultaneously satisfied. So in the interest of time, I'm just going to skip the technical details of Vitals. But what I would like to show here is, as soon as a station wins, it only transmits haptic frames as opposed to augmented H plus V frames in the earlier case. And when the access point wins, it's going to transmit kinematic frames. And only when the piggybacking happens, the stations send out video frames, right? We saw earlier that when piggybacking happens, there is definitely no collision happening between the stations. So the stations exploit this collision-free opportunity to transmit video frames to make sure that they reach the receiver on time, as well as with the required 98% reliability. We conduct performance evaluation of vitals, both using simulations as well as emulations. And we are interested in many parameters, but what's of primary interest is, does vitals bring any sort of latency improvement at all when implemented on real systems? We do some objective evaluation to begin with. We also build a mathematical model to characterize the performance of vitals framework. And what we do here is measure the packet durations that result from a vitals framework. So S corresponds to measurement from simulations, and M corresponds to model estimations. And as you can see, the packet durations that are estimated by our model, they corroborate very well with what we measure in simulations. So that sort of gives analytical guarantee of working of vitals. And also, we measure or we plot the probability distribution function of channel access latency. So as you can see, the channel access latencies of both access point as well as stations fall below, or at least the mean falls below 5 millisecond, which is nice. And there is some sort of asymmetry between the means. That's because of the access point being gentle to other stations when it wins. So essentially, when the stations win, they transmit, as well as when the access point wins, then there is also an opportunity for stations to transmit. So the inter-channel access latency of stations thereby reduces. So we go further. We implement both vitals and visual haptic multiplexer on our real test bed. And what we see is that both haptic latency as well as kinematic latency of vitals, which are the solid lines here, they reduce significantly in comparison with visual haptic multiplexer. And also the video latency of vitals is also significantly reduced in comparison with visual haptic multiplexer. However, the downside is after 8 Wi-Fi stations or after 8 robotic arms, the video latency sort of blows up. That's because of an unoptimized parameter of vitals, which we did not really work on back then when we were plotting this. But even otherwise, at 8 stations, if you look at the latency of visual haptic multiplexer, right? So the haptic plus kinematic latency is already about 30 milliseconds, right? Which is already bad. So even with VH multiplexer, you cannot operate beyond 8 station anyway. And we finally have subjective evaluations where we performed a lot of experiments with human subjects, and we collected their experience. So the experience is graded between 1 and 10, where 1 refers to the worst experience and 10 to the best. And we compare the performances of visual haptic multiplexer and vitals. So we also have a variant of vitals that we call vitals optimal, which essentially chooses the optimal value of the parameters of vital. So as you can see, vital gives slightly a better performance with respect to user grades in comparison with VHMax. But if we choose those parameters optimally, then the performance increases drastically, and that's what we are looking at. So this current work on vitals is under revision in a very good journal, and we expect to have this online in a few weeks starting now. So that brings me to the conclusion of this talk. So we saw tactile internet. It's an upcoming technology with lots and lots of promises, and it has a very rich set of use cases, which will pretty much benefit each and every aspect of our lives. However, it also brings together a lot of challenges, the primary one being ultra low latency challenge, which is sub 5 milliseconds, and it's really daunting. So To address this, at least at the first and last mile level of Wi-Fi, we did vitals, and we showed its design and also its improvement over state of the art. And that brings me to the end of the talk. Thank you so much, and I'm open to questions.
You are muted.
Professor Lal has a question.
Thanks, Vineet. Interesting presentation and nice work. A couple of questions I had. The first was, what model are you using for the traffic? Because you have a mix of video and kinematic and haptic data. So is there a software modeling tool that you've used for that, or did you build a model on your own?
Right. So right now, as concerns a traffic generation model itself, we are looking at very deterministic traffic frames, right?
Mm-hmm.
In the sense that haptic frames always come with 1 millisecond inter gap, and the video frames always come with about 30 milliseconds of interframe gap. This lets us do a proof of concept. However, in future, we would like to introduce slight bit of randomness to be more realistic in terms of traffic generation policy. And that's concerning how we are generating traffic. And about the implementation itself, Vitals is built on a custom Mac implementer that we built on our own. And the reason for this is when we started out, NS3 still did not have any Wi-Fi 6 packages, and that was really a limitation. So we thought, instead of delving into NS3, which has like a very vast database, why not we focus on this niche of getting a Wi-Fi 6 package to working? And that's what we did. And we have also open sourced this a custom simulator, and people can easily access and build on top of it.
Yeah, so I encourage you people to download that, evaluate it, use it in the work that you do. And one more question, that's the genesis for the question I just asked. Your PDF for latency turned out to be bimodal for both stations and access points. So is that characteristics of the protocol, or is it because of the data, the traffic pattern that you've used, or you haven't looked into that?
A very interesting question. So this bimodal nature is because of the traffic generation itself. So what's happening right now is there is a bit of randomness in video traffic generation across stations. Within a station, they're all getting generated very periodically. But when it comes to across stations, so there's a randomness, but on the scale of on the scale of, I would say, 1 or 2 milliseconds. So what that means is, once you start the simulation, all stations pretty much generate video frames in and around the 1 or 2 millisecond gap. So you have this sudden flurry of video frames, and at times there is none. So which means if you look at short-term latency characteristics, you will have small windows where all stations would have generated video frames, and that results in this part of the graph. And then you have silent period where there is only a continuous haptic frame being generated, and that results in this part of the graph. So going forward, what we would like to do is also randomize frame generation across stations, because that's how it should work in reality.
Perfect. Sounds good. So I'll encourage the teams here to certainly download what the work that Vineet's team has done and try to use it in the works that they do. Thank you so much, Vineet. Excellent work.
Thank you so much. Thank you.
Thank you so much, Dr. Gokhale. We have another question from Najib. She is probably joined online. Can this algorithm implement with 5G wireless channel?
Yes, definitely. So while the testing itself is done on a Wi-Fi 6 package, the underlying principles of this algorithm can very well be generalized to any sort of a first or last mile link, right? Whether it is 5G or Wi-Fi, doesn't matter. So it's just a matter of porting the implementations from the Wi-Fi 6 simulator, and then writing a own, let's say, custom package that is compatible with, I don't know, 5G network, 5G backhaul. And then vitals should be ready to be tested on other sorts of communication modalities as well. I hope that answers the question.
Any further questions from any other participants? Okay, thank you so much, Dr. Gokhale, for this informative talk. We have another
Thank you so much.
expert. Thank you. We have another expert from TU Delft. Lalokji, can you please share the screen and come down to slide number 6? Yeah. So we have our next expert talk by Dr. R. Venkatesh Prasad, who is Associate Professor at the Delft University of Technology, Netherlands. He has been selected as an IEEE ComSoc Distinguished Lecturer on IoT for the period of 2 years, 2016 to 18. He is a fellow of IITD, a senior IEEE and ACM member as well. So he would be giving us more insights onto tactile internet and setting up of a test bed on this. So over to you, Dr. Prasad. I welcome you on board.
Thank you. Thanks for inviting us, and then also thank you for your kind introduction. Maybe I'll need to share my screen. See my screen?
Yes, sir, we can see your screen.
Okay, great. Okay. Did it go full screen now? Perfect. Okay.
Yes, sir.
So, yeah, this some sort of catchy title maybe, yes, there are many problems to take on. And then, of course, I'm working with Vineet and one more of my colleagues, case group. So this work is some sort of a general outlook of what is happening, and then what is the direction in which we are thinking these days. I don't want to dwell on again the same things, but just to get to the point. So we know that there are 3 domains, and then you have to do.
Sir, sorry to interrupt. If you could be a bit louder, maybe adjust your mic.
Yeah. Okay. Then I need to see if I can do that. No. This. Yeah, maybe. Right. Yeah. Can you hear me now?
Yes, sir. This is better.
Yeah, but I don't hear. I don't hear back. Hello. Yeah. 1 second. I need to do that. I think. Select. Yeah. Hello.
Yes, sir.
Yeah. Now it's fine. You are also able to hear me well, right?
Yes, sir.
Okay. Great. Sorry for the hiccups. So when we look at this whole domain as such, right? So what we thought was that let us not really mix up completely the whole chain from one end to the other end. So what we wanted to, let us say, address these domains in isolation, so that we can pinpoint the issues and then solve there. Basically, you are going to get some sort of local optima. And then when you put them together, probably, or at least you
you wish that there will be some sort of a global optima in the sense of application and the quality of experience or quality of service. So you already have been told about telesurgery and many other applications. So something that I would like to bring here is that tactile internet is basically a great unifying application wherein lots of these solutions that we come up with can be used in multiple domains. For example, vehicle-to-vehicle communication or automated vehicles, for example. Fine telesurgery is going to be always the holy grail for tactile internet applications. But there are multiple other things which are bit less critical, but equally challenging, right? So in that sense, for example, if you look at the virtual reality or augmented reality, learning aspects, for example, and then treating people with disabilities in many such applications, this is going to really a very nice tool. The question is it possible to generalize? And then is there a possibility of identifying some of the common modules? So this is something that we were looking at. Yeah. So let us see what aspects that we need to really bring. As I said, this is a great application that brings lots of areas or lots of challenges, multiple domains together. So for example, if you take, because people are going to be the ones who are going to use this application, so you have to put human and human psychophysics in one part. And of course, you have the control system and mechanical systems there, and the distance is involved because it's going to be remote. So you need to also talk about communication and signal processing aspects. And the funny thing about this is that human psychophysics basically gives you the stimuli and response relationship which you need to catch, and that need to be considered by the mechanical or the control system, and use that to design and then analyze the stability. Of course, you would like to have the stability of these systems that we build. And of course, you have at the end, how do we communicate these modalities? Protocols, Vineet already talked about one, and this multidisciplinary aspects of tactile internet is going to be a very important aspect that provides a fertile ground for lots of research, but also it makes it very difficult to come up with very creative and easy to implement applications. So ultimately, what we need to do is that we need to have the cross-domain synergy, and without which you will not be able to come up with a good system that can demonstrate and also provide services to the users. What we did is we took the master domain where the control things happen. So are the glove or the force feedback systems and tactile devices. So that's something that we wanted to catch. So this picture is basically from what we from 1918.1 and what we really presented to the standard. So as I said, we wanted to make it modular. And in that sense, so we said, okay, 5G, URLLC networks, whatever that we are going to have in the future, so they all can be clubbed together and look at only the last mile and the first mile, because most of the times we will not really have control over the network, the core network, because it depends heavily on ISPs, and 5G is still coming up. And I always ask one question whenever I meet people who are working on 5G is that, what is your definition of 5G? So I ask the same question to everyone. Probably you can ask me the same question, but I don't think I have the answer. Jokes apart, so the core network is really difficult to manage or also play with. Apart from what the ISPs provide us, some of the knobs or the tools to play around. So what we have in our hands is the last mile, because or the first mile. So where we have really have an opportunity to unify lots of different use cases, different modalities, and also how do you code, how do you transmit, and how do you manage before the data before you put it into the core network, right? So this is something that we were looking at, and how can we really make it generic, modular, and also plug and play. So what Vineet was talking about, Wi-Fi 7 is one of that thing. So once we have once we have the diverse use cases, how do we classify and do things? So for example, the big picture that I would like to present here is that there are multiple ways of looking at the tactile internet applications. For example, human machine in the virtual world, and machine to machine, human to human, and for example, tele repair, tele maintenance, or exoskeleton that we build for people with some sort of disabilities. And then also sort of disaster management, where you want to remotely operate some of the earth movers or big equipments, right? So they are the ones which you see on the left side. And also you have the teleoperators and physical and virtual domain, which you could see on two ends here. And you need to really work in different ways, machine to machine, to human to machine, to human. So this is something which which actually I would rather say that it gives us lots of opportunities to work on many of these problems creatively. That's something that we are interested in. So again, to stress, cross-domain synergy is crucial to make these applications useful. What we did was that we did one simple test bed. So it's very, the idea should be that it should be easy, and also it should be really generic and take into account the network aspects. So let me play this. So you could see that we have the Falcon force feedback device, and we have the virtual world, but you see two ends here, two ends of the applications. One is the control domain, the other one is the master domain. And of course, we kept it next to each other so that you could see how things operate. The idea is that you can abstract the whole core network. Sorry, core network with switches and other things in the background, and control the way the packets are dropped, the way the delays are introduced, the latencies are introduced in the core network, and also work at the edges, how exactly these applications, when you run these applications at the edge, how they behave, without really looking into the Wi-Fi 7 aspect here. So Wi-Fi 7 is one more module that comes in between, for example, these two domains, and then or before the or after the core network. So we have switches and others. Probably you could see on one of these tables here. So then from there we wanted to work it out. So the other thing that we were looking at, I will show you a simple module at the end. So we are also trying to use some simple gloves, and then also we are trying to build robotic hands. So we came up with this architecture, and then some amount of implementation with bringing the network or emulating the network in between, and so that you can have multiple types of solutions, even the control algorithms and perceptions, or even faking the physics. That's something that we are working, so that the users will not really feel the delay or the motion sickness, for example. So this is one thing that we came up with, and then we did lots of tests. For example, this is interacting with a virtual world, and the feeling um, is really real with the Falcon device, where you actually get the force feedback, and also depending on the friction, you will also see it's going to be almost the real experience that you see if you are operating a machine, an earth mover, or a JCB, for example, how this operator feels. So so we have a block here. So we are trying to move it around. And this video actually shows when we introduce some delay, how things work out. So here you see that things are smooth, and the operator is able to handle it really well. Now things will start becoming very tough. You could already see the jumps, and at some point you will also keep watching the hand. The see already the shaky thing. So the smoothness with which the operator was able to handle earlier is already gone. Yeah, you see that the stability has been yeah, it's almost, yeah, actually it's not purposefully done. It looks like that, but the problem is that he's not able to control because of the delay. So the device hits back, and that's where the problem occurs. So with this test bed, so what we did was, okay, if it is congested, what is the feeling? If it is not congested, what is the feeling? You could see that more or less a rating of 9 is what you see across different subjects. I know that there's no brainer. As soon as you introduce the delay, you will see that, but it's always nice to put it down and then experience it, and that already gives us much more ideas of what exactly the real feeling when you work out such an application over the internet. And also the emulated network, you can reuse it, exactly the same settings across the users, and also control how exactly the core network behaves. So this is something that we worked on, and maybe I will also show you the other device that we started building. I could have showed it, but one of the wires got cut. So when you trying to make something which is much less expensive, this is what is going to happen. So here is basically we implemented 2 fingers with just simple 2 servos, but you are able to mimic the fingers so well. So that is something that we really worked on. And the actual device, the state-of-the-art device, if you buy it, it's like 50,000 euros. So still we are working on the evaluation, and if you are able to get, let's say, some if you are able to get the resources, probably we want to make it like 2,000 euros device, which is much easy to buy and then experiment. So the second topic that I would like to look at is Wi-Fi over 7, tactile internet over Wi-Fi 7. So what we did is that whatever that Vinit was talking about, really working into the Wi-Fi 7 access point and the protocols itself. So we wanted to see whether we can do something even before getting into Wi-Fi 7 aspects, whether we can do something at the devices. So the philosophy, or at least the way I look at it, is you make things simple and stupid. Most probably such solutions work very well. So the idea is this: you have multiple devices or multiple sensors, so they all produce data, and then those things will be in the device queue. So different devices have their own queue, and then they need to access the wireless um, uh, gateway, the access point here. So, and the access point also will be getting the data from the other end, the force feedback, for example, and it has to distribute it to the actuators. For example, the actuators or the buzzers or the vibrators on my glove. So, of course, we know that collisions are going to happen, and then we all know if you keep buffering, then you are going to have the problems anyway, because the latency will start increasing. And probably this is something like old wine in new bottle. Voice over IP, 20 years back, I was working on that. So we all know what to do here, right? So we use the same thing, and very simple technique, and then we try to come up with how things work. So now implement very simple technique, and then use the test bed that we have and test it out how this works out, right? So we came up with something called NoBus, basically no-brainer application or a algorithm. So the idea is that the normal system without this simple technique is we call it as, let us say, vanilla Wi-Fi protocol, for example. So if you have a device which is, let's say, this brown or the blue, so all their packets will be queued. So instead of that, what we said is that the data is not really random. So when you have a let us say a touch or your finger movement data, so it's not going to have from one data sample to the other set data sample, things are not going to be completely random. So in some sense, so you know that instead of a curved motion, for example, if I want to move my hand in a sort of a curvy fashion, so if you lose some of the points, you may linearize, you may jump, but still you're not going to lose much of the information. So instead of having many samples queued, just transmit the latest frame. I know Kerani had worked a lot on TCP/IP. He knows much more about this, the techniques that people used to get the TCP work in different situations. So something similar, that's what we did. So here are some nice results. So for example, without any of these our implementation or our protocol NoBus. So if you see that when this number of stations increase, you see that aggregated MAC protocol data unit size, it keeps increasing. And then also the latency, that's what you could see. Uplink, downlink, approximately both behave in similar fashion. And now you look at the right-hand side picture, for example. So the position error, without really implementing, if you want to really transmit all the data packets, all these sample points across, you could see that the RMS error starts increasing. It is because the idea is that when you give a command, you also would like to get the immediate force feedback. or at least passive feedback, right? So if that doesn't happen, then assuming that if I want to, let us say, hold my cup, so because of the delay, you'll be pressing the cup much more. So then suddenly you realize that you're pressing the cup and then you hold it, you release it. So there is a possibility of dropping it even, right? So just as a dumb example. So that's where you start losing and the position errors start increasing. But if you just drop it, yes, the error increases, but very slowly compared to the vanilla Wi-Fi. And also the number of samples transmitted. Of course, we are dropping the packets. And here you could also see that if the gateway is congested, the packets are also dropped here. So the advantage is that even though you drop the packet, and if you drop further packets, still the error is less because you creatively select the important data samples. That means you reduce the delay. So you could see how this was done here. I don't know whether you hear the sound. Okay, so probably I'm not going to change it. You basically you see the you could see that things are really unstable. What we saw earlier, right? So it is unstable. Now, what we are going to do is, yeah. So the no bus is added. So the delay is again the same, but the unstable system became almost stable. You could see that yes, there is a little bit of difficulty. You could still see that, but it's definitely not that bad as what it was, right? So you could also see the subjective grading, and it's much better compared to the normal vanilla Wi-Fi. So to conclude, of course, there are multiple problems. We have to definitely take one by one and probably together, as we said, it's interdisciplinary. Haptic coding is another one where you may reduce the number of data points that you want to send, basically the packet sizes. Of course, perceived quality is something which is really important. We can play around a lot, probably at maybe after, let's say, 3 to 5 months, we should be able to talk about this faking physics. And then, of course, the testbed is a very important entity. And I feel that there is so much of work that's being done in IIT Delhi. Probably if there is a testbed from there to here, or somebody from there to here, for example, connecting and then working on our testbed. I know it takes a bit amount of time to do it cohesively, but that can be a very nice thing for us to learn. And is it also possible to build less complex and less expensive devices? As we said, text is one nice example. Of course, my experience of working with a startup 20 years back, we should not target what we have now, but I think what can be the future. So I think we should already start working on it. By the time the devices and others become less expensive and start slowly getting into user domain, for example, Wi-Fi, everyone has a Wi-Fi access point now in their houses now, right? So so we have to really work on the new standards and new equipments that are going to come. So with that, we should be able to keep really pace with the requirements of the future. So I would rather solve these problems and then look forward to the future. Thank you so much for listening to us. If there are one or two questions, I will be able to take it up. Thank you.
Thank you so much, Dr. Prasad. Are there any questions? Anybody here? Okay. Thank you so much, Dr. Prasad. Of course, IIT Delhi looks forward to collaborating and taking this work forward. We'll get in touch sometime offline. Thank you so much.
Thank you.
After our technical experts, we now have our next speaker. Dr. Prasad, could you please stop sharing your screen? We have our next speaker, Mr. Vishnu Ram. He has a hands-on experience in the field of telecom industry for more than 2 decades now, and he has been coordinating the AI/ML in 5G challenge across the globe. He will give us further insights to the global round to which our winners would be now entering. Over to you, Mr. Vishnu.
Thank you so much, Pimi. I will take the screen. Yeah.
I'm so sorry, we are running short of time. So I request you to please take a note of that.
Absolutely, yes.
Thank you.
All right. So let me see if you can. That should be good. All right. So yeah, Pimi is the boss. So I'll go fast. Build-a-thon 2022. Where do we go from here? And that's what we will discuss. So here is the introduction. Build-a-thon we are running as a problem statement in ITU AI/ML 5G challenge. This is a global challenge. There are many problem statements. And this particular one, that is Build-a-thon, is hosted by Focus Group Autonomous Networks. So that's why you're hearing again and again about closed loops, autonomy, autonomous behaviors, and all that, the low latency and so on, right? So our aim is to demonstrate and validate important use cases for autonomous networks, and proof of concept implementations and tools are an important part of it. So, so I will skip over the rest. It is open to anybody. Participant could be a student, startup, small enterprise, university, prof, everywhere. Currently, I think we have about 26 teams across the world who are participating in this particular problem statement. And right, so other things already Vinti in her first talk already covered the rest of it. Okay, so what are the tasks for the participants? Select a use case. That is, I think most of you have already done. Professor Azad talked about the use case. You select that use case, draw a design. I don't think many of you would have done this. I can help you to do that. The winners, whoever comes out of it, I will help them to do that. Upload their design to GitHub. So again, I don't think you have done this, but I can help you to do that. The winners, I mean, from India. Use the reference tool sets to demo. I think many of you would have the demo now, and there is links here which you can use as a reference point. Look at the highlights here. You can see the last date for submissions is on 28th October. Please, the winners who are coming out of today, I would request them to submit to ITU by 28th October. You can send your solutions to me and I will make sure that I can help you to upload. There's a judging and demo event globally on 7th November. Reports would go out to our ITU global audience and study group 13, who is the parent group. That's happened by November, December. That's my job. No worries there. There is, however, grand challenge finale happening on in December 2022. We have a grand challenge finale. So you are all welcome to do that. And if you are a winner out of 7th November, then of course you will be invited. There are recordings of the global events which I have put here on the right side, and India events, of course, Vinti already covered all this. How do you win global prizes? So you have to create a focus group document. I will help you to do that. Again, the winners from today, we will help to create this and put this, submit it to ITU. You can make a cool demo video and upload it, extend the solutions, and basically publish notebooks, your code, I mean. We also have opportunity to write a paper, but that comes later, and we will talk about it after maybe the dust has settled, so to speak. There are some sample requirements that I talk about here. So what we do is to create a use case out of it, and that we will use that to make a design. So if you go to the landing page of the IIT Delhi event, I mean our India round, you see this figure, right? So this is the figure that you will see. And based on that, we derive certain requirements for this particular use case. For example, indent prediction at the edge. So Arzad already talked about this, but that's a critical requirement for this particular use case. And then we talk about other things like application-specific constraints, how to capture it. For example, Munib talked about in the previous workshop, if you remember. How do you hold without breaking or deforming the object? Then it is critical for that AN enable integration of optimization mechanisms. For example, AI/ML models. This may be very obvious to you, but for formal requirements for the use case, we have to capture it this way. Okay. So then what do? We make a design. First in the design, we make the actors. For example, Arzad talked about end-to-end intent, haptic app constraints, optimization mechanisms, edge computing platforms, and app parameters. So these are the actors in this particular use case. Then from there, we make the relationship between the actors and make a nice design, which appears something like what you see here. All right, what happens afterwards? We basically push for standards in this space. This particular activity, whatever we are doing today, is pre-standard activity. But what happens afterwards? We can go for India-specific requirements, look at frameworks for applications. Some of these things we have done before, like for example, data repository, model repository, indent repository. So these are things which we have discussed previously in other groups. And the same thing we apply here for framework for applications as such. Then for framework for intents, how to capture this, what is the format, what is a acceptable format for intents, and benchmark parameters. As I talked about edge viability of various applications, and then I think Vinny talked about this game integration, right? So one step further, if you take from there, you look at metaverse and testbed integration for tactile internet apps. These are some of the things which we can look at as the next step. Maybe next year, we look at some of these things. I just mapped what happened today. For example, if you look at this picture from focus group, you look at our what happened today in our event, then you can map this figure which you see in focus group to this edge viability template and object detection template to be in this repo that I talked to you about. So there are ways to map it, and if you map this in a nice manner, then you are going to win. What is that? 5,000 Swiss francs. That's the first prize. So this is a global prize. It awaits you guys. I mean, it's across the problem statements, so that has to be clear to you. But you still stand a chance. All right. So then, if you are worried about GPU, no worries. You are all covered. ITU provides GPU access. It's free of cost, and we provide Jupyter and Python kernels already. So in case you want to tune your models, let me know. Okay, so here is the global event on 7th November. Please join us. Winners from India from today, they should submit the reports please contact me, and that should be done before 28th October. I am not a last minuter, so I don't do anything last minute. It's impossible for me. So please contact me beforehand. We'll work on it. There is still time. We will finish the reports and submit it on time. Next year, what happens next year? If you have inputs, please talk to me. I think some of the things which I talked about here comes in as build-a-thon for next year. All right, so that might happen. So other than that, you can talk to me. Thanks a lot. Good luck to all of you. Back to you, Penny.
Thank you so much, sir. And thanks a lot for making it so quick. Next, we have Munib, who is a PhD research scholar at IIT Delhi. He has helped us in framing out the problem statements and evaluations as well. I now request Munib to kindly give us the details on this part. Are you online, Munib?
Hi, good afternoon, everyone.
Hi, good afternoon.
Am I audible?
Yes, we can hear you.
Okay. Just give me a second.
Munib, we are running late, so I request you to keep it a little quick.
Yep, almost there. So yeah, so I hope this is visible. So I
We
won't
can
take
see
much
your
of your
screen.
time.
Sure, thanks.
So I want to talk about how we did the submission. So as you are aware that we had a pre-evaluation phase and that followed a final submission. So we have divided the points in the ratio of 20 to 80. Thank you. I want to thank all the participants, the contributors, the management who contributed towards efficient conducting of this event. I wanted to tell the participants about the FAIR policy that we have followed. The sole motivation behind pre-evaluation was to help the participants understand that their submissions would be auto-graded. And we have deducted 25% of the actual marks for pre-evaluation when a late submission was sent to us. The final submissions have been graded in the following way. We have given accuracy a 75% weightage. The time of prediction that the participants, the model submitted by participants take, they have been given 15% weightage, and the compactness of the size of the model itself has been given 15% of the weightage. So I guess that'll be it from my side. If there are any questions regarding the submissions, I mean, I think the participants would be having it. Please tell me.
Any question from the participants? Is there any confusion? Then please ask. Otherwise, we'll go ahead with the declaration of results. Okay, thank you so much, Munib.
Thanks. Over to you.
Yeah, thank you so much. So next, our professor in charge, Professor Brijesh Lal, would give us some more insights to this entire event, the Build-a-thon and the activities and the results. So I would now welcome Professor Brijesh Lal.
Yeah. Good evening, everyone. Hope I'm audible. Okay, so this has been quite an enlightening and enriching experience for at least the team here. I am sure the participants also were fully able to utilize the opportunities that accrued because of this Build-a-thon happening. There will, of course, be a formal vote of thanks, but I take this opportunity to thank you for making this happen. As you might have already understood from the talks that you heard now and during the the mid Build-a-thon workshop that we had, that haptics is slowly but surely evolving as something that might be the next big thing in terms of processing solutions, applications, the kind of thing that people will want to focus on. So over the years, what's been happening is we hear a lot about AI, ML, you hear a lot about 5G, but all of these things are essentially tools or enablers. And what they actually enable are applications and capabilities that ride on top of them. There's been a huge improvement in the way we consume and are supplied with video and speech and text. There's a sea change if you look back 5 years, 10 years. All of that has reached a level which is quite much better. If you recall, even 5 years ago, what was happening was that the display capabilities, for example, were way better than the cameras that used to come with smartphones. So at that stage, there was this huge thrust on building super resolution algorithms in video. So the content was being created, but the content wasn't good enough for the display capability that you had. Today, most smartphones can create content which is of quality better than your displays can render. So a lot of work that happened in the area of video processing to improve the resolution now does not make that much sense. There are interesting scenarios that continue to exist in the area of video analysis and processing, but it is slowly but surely becoming less and less challenging in terms of the quality of research that you do. On the other hand, however, what is happening is that the proliferation of haptic devices and the kind of use cases that are now enabled because of haptics capabilities becoming a reality is becoming the next big thing. So there is this need for shared experience. There's this need for more immersive experience in communicating, in sharing information. So haptics, and the other thing that's becoming quite popular in the research community is 3D. So you will see a lot of thrust in these areas. So this is why this area is slowly gaining traction. But what's even more important is the kind of things that you can do. In Professor Prasad's talk, the part that I saw, he did mention about 3 broad areas that certainly need a lot of work for haptics to be able to deliver on the promise that it seems to be giving us right now. The first was mechanical and control. The second was signal processing and communication. And the third was perception related psychophysical, because some of the content will continue to be consumed by humans. So you need to do research in the area of mechanical engineering to create more optimum devices in terms of how they can be used. So the weight, the size, their fit and feel, all of that has to improve if they have to become commonplace. 3D TV has come and gone many times, but it has not found too many takers. So the reason for that is it's quite inconvenient. You put on glasses, the size reduces. So while you see a lot of 3D movies, you don't see the same kind of excitement when people start talking about 3D TV at our homes. And that is something to do with the device availability. You have to wear glasses. Glassless displays bring the resolution down to half immediately. So that is an area that is finding hard to become popular. Headsets, the Oculuses are again inconvenient devices. So even though they give you potentially an experience which is much higher than regular television, they don't become popular because the device has some inherent limitations in terms of how humans consume them. So similar things continue to exist with haptic devices, more so for haptic devices because they are becoming popular, more popular of late. So this is where the mechanical and the control work is going to happen, and a lot of it you'll see a lot of it happen. A related area is standardization. Unlike current robotic solutions or devices that people are building, all of them are in some sense standalone. You're not expecting them to work with other devices. You get an end-to-end solution and they do what they promise. From the same vendor, an end-to-end solution, the controller and the robotic device that will perform the manipulation that you expect of it. All of it, so it's a one-stop shop. But that is a very inconvenient way to generate volume. So interoperability is something that will need to be built in. So the robotic devices of the future will need to be interoperable, which means that they will evolve into having some common standards in the way they are built. For example, humans have evolved to have 4 fingers and an opposing thumb. You might see machines doing something similar. The other thing that will happen is the middleware, the operating system that you'll have to build for such devices. That will also have to converge towards an area where more and more people can use it and therefore build applications on top of it. It's very difficult for any content provider to build content on 15 or 20 or 30 different platforms to make it popular among the population, among the people. So in this area, you will see improvements in control algorithms. You will see improvements in material. You'll see improvements in how the mechanics are handled, but you'll also see a thrust towards standardization, and you will also see a thrust towards an emerging operating system, a kind of a scenario where more and more applications can be built a lot more easily. The other area, which has been the area of interest for this particular build-a-thon, is the one related to signal processing and communication. When people used to transmit speech, they used to worry about certain numbers related to latency. Then when people started transmitting video, they started worrying about some numbers of bandwidth. Now with the advent of haptics, what has happened is that the latency numbers that used to trouble engineers and designers are easy to achieve. You have new benchmarks that have been set. 5 millisecond latency and lower is what you need to achieve. From hundreds of milliseconds, you're down to 5. So there's an orders change in the expectation of the latency. All of this was extremely exciting when 5G was promised to the world with very, very low latency numbers. But when engineers and researchers actually got down to making some haptic devices work across networks, they realized that some of those numbers are difficult to achieve. And that is how some of the work, interesting work that happens out of Professor Prasad's lab, the kind of work that Vineet is doing, all of that becomes a reality. The kind of work that we do in our lab related to the physical layer and implementing of the MAC are all examples of why 5G claims a certain latency, but it's not a plug and play thing. You don't deploy 5G and suddenly the haptics devices are up and running. It doesn't happen that way. There's a lot more work that needs to be done. But what 5G did was make the people working in this area realize that these latency numbers are indeed possible. And therefore, suddenly you see a thrust in the research and engineering work that's happening in this area. So you see a lot more people trying to actually engineer these low latency numbers that everyone's talking about. And then there is signal processing. When you want to achieve these numbers, you then start to communicate information from one device to another across a network. And at that point in time, you require to do signal processing to achieve 2 fundamental tasks. One is to convert the signal into a format that is amenable to the capabilities of the network. And 2, it allows you to perform analysis which can then aid inference and recommendation. These applications will become usable only if you can make predictions based on them, you can make recommendations and inferences based on them, if you can actually transport them after processing them at the endpoints where they are consumed or generated. So signal processing is now seeing a lot of work being done in this area. The talk by Professor Khairani talked about how we are trying to understand what is the amount of information that is present. So that study will tell you what is the kind of, or the level of information that is present. Signal processing will help you convert the data that you are generating from these devices to come close to the amount of information that we are actually targeting. So signal processing will see a lot of this happen. What will also happen is that you will see a lot more machine-to-machine communication. At this point in time, the struggle is to enable use cases related to teleoperation. So you have a human at one end and a machine at the other. But tomorrow, when this matures, there will be opportunities for the endpoints, the robotic arms with hands or claws mounted on them. They can do multiple tasks. So you could have a server, potentially a machine, which can make these endpoints accomplish different kinds of tasks. So you will have a machine communicating with another machine. The teleoperator will also become possibly a program rather than a human trying to control the other endpoint, which is again a machine. So machine-to-machine communication is also going to become popular, and therefore the need for inferencing, recommendation, prediction, analysis, all of that becomes paramount, and therefore you're seeing a lot of work and interest in this area. Finally, there was talk of psychophysical. The human is not leaving the loop yet. So it's not only machine-to-machine communication that haptics enables. A large chunk of traffic, at least in the near term and in the medium term, is going to be, at least one endpoint is going to be human. And humans perceive. For them, it is as much about information as about the way it is presented to them. And therefore, these studies related to quality of experience, about creating signals so that they create the right perception or the right feeling, will continue to be important. So psychophysical studies will continue to form a very, very important part of the kind of work that will happen in this area. So over the next few years, you should see a lot of research and engineering activities spawned around haptics. So the days of high quality robots being standalone will give way to robots, haptic devices having wider proliferation, them becoming interoperable, them having some degree of intelligence, them having the ability to convert data into information, transport it to a distant location, and then either make inference based on that or perform tasks based on that. So I think the area is it's just starting out. It's in a nascent stage. So even though you might see some high quality robots, but as far as the area of haptics is concerned, this is simply the beginning. A lot of action should happen over the next 5 or 10 years. And 6G might be the first communications generation where you will see relative widespread deployment of tactile internet capabilities. So with that, what I'd like to say is, it's good that we seeing this kind of interest in this area, and the time that you're spending in this particular domain is not wasted. As a matter of fact, it will find a lot of utility in the times to come. You will have a lot of challenging engineering and research problems to address. And I wish you all the best, and thank you for participating. That is all that I want to say right now. Thank you.
IIT Delhi is grateful to EU ICT standardization for initiating this challenge. EU ICT standardization is aligned to ITU, IETF, ETSI, and 3GPP. India EU ICT standards is vigorously promoting research in academics and translating that work into standards. So that is what we are all about here over here. And of course, Mr. Arun Mukherjee from EU ICT standardization was the main mover who actually moved this whole challenge and brought it to this point. I'll hand over to Pimi now to make the next announcement. Thank you.
Thank you, Professor, and thank you, Binti ma'am. I now request Mr. Arun Mukherjee to please come forward for a vote of thanks.
So thank you, Pimi, for this opportunity, and thank you, Professor Lal, also for this opportunity. It's been wonderful, I think, what has been going on. So just to say, I was in Germany recently with 4 young scholars, very much like us sitting here, and they were from IITH, and they had won a hackathon also a couple of years ago before the lockdown. I just wanted to support what you were saying, sir. It's one of the largest startup events which they had attended, called Bits and Pretzels in Munich. And though there were e-commerce startups, etc., the tech startups, more than 60% of them all were robotics, AR, VR, machine learning. It was amazing. And the boys were very excited because they too were into robotics now after 2 years. So I think it is very much the future, sir. Yes. And I think all of you should pay heed to what sir has said also over here. It's going to be the future. So I will not talk about myself. I think Vintiji has already spoken about me, and Pimi. I'll just briefly, big thank you to Professor Brijesh Lal. He's a professor at Bharti School of Telecom. I don't need to mention it more. And I believe, sir, that you have been responsible for the setup of the Haptics and Edge Computing Research Lab over the past 3 years, and architected the Build-a-thon challenge here, including the design of dataset and problem statement formulation. Sir, thank you for your guidance on this. Professor Arzad Khirani had mentioned he's stepped out, he had to go somewhere else, but big thanks to him. I believe he's an expert in edge computing and low latency application, and he's significantly been contributing to standardization activities. And I'm very happy that I'm going to be doing a project with IIT Bhilai along with him also on LoRaWAN. So I thank him for having architected the MEC testbed in the Haptics Lab and also mentoring the Build-a-thon team over here. So wonderful. A special thanks to Professor Venkatesh Prasad and Dr. Vineet Gokhale, both from Delft University of Technology in the Netherlands. They have participated as the experts from the European Union. Our project looks forward to bringing forward people from Europe to share experiences of what is happening there and, collaborating here. In fact, Professor Prasad has also, if I may say so, been very instrumental in getting ISRO and the Netherlands Space Research Organization to collaborate, and is very much in the eye of our Prime Minister also. So thank you so much to both of you. Big thanks to Mr. Vishnu Ram. He's a TSDSI and ITU consultant and the standards champion, and an IIT Delhi alumni, always very highly esteemed people. He spearheaded the formation of the regional team and provided his expert advice through all the meetings and public forums aligned to the ITUT Global Challenge. Thank you, Vishnuji. And also many thanks to Dr. Pimi Gandotra. She's doing a postdoctoral work in many fields with Professor Lal and Professor Arzad. She's been the voice and face of the challenge, I believe. Yes, thank you, Pimi. Thanks to Muneeb. He's a research scholar in Haptics and Edge Lab. He was the techie in the Build-a-thon with support from KAIM. So thanks to both of you. To Ms. Manrika Malhotra for the logistic support during the 3-month period of the challenge. And to Gautam Tiwari, research scholar in IoT and 5G lab, a problem solver for all technical and logistics questions. Thanks, Gautam. Thank you to Gauravji, Gaurav Shukla. He's the project manager in 5G and Beyond project. He's an MEC expert and coordinator of this Build-a-thon challenge. Along with managing the many activities, Gaurav also built and maintained the website for the challenge. Thanks, Gauravji. Also, a special thanks to my colleague Alok Chaudhary for his great support on the online platform and smooth operations and arrangements. And last but not least, a special thanks to Savita, Dilip, Anita, Rahul, and Sagar of IIT Delhi for the arrangements and great support. And a personal thanks to Vinti ji. I think she chased me tirelessly. So I know I was very elusive, and I apologize for that, Vinti ji. So thank you very much for all that. And I wish you all the very best over here. Thank you.
Thank you, sir. I request you to please stay back. And I would now request Professor Lal, Gaurav sir, and Vinti ma'am to please come forward for the mementos. Okay. Mr. Mukherjee, I request you to please present the memento to Professor Lal. So, Vinti ma'am, I request Vinti ma'am to present the memento to Mr. Mukherjee.
Thank you. I'm not a speaker, actually. I'm not deserving of this. But thank you.
Okay. We don't have Professor Azad here, but I would request Professor Lal to present the memento to Gaurav sir, please.
Yeah, Gaurav.
Mr. Mukherjee, would you please present the memento to Vinti ma'am?
Thank you, sir. Don't deserve it. Thank you.
Next, I request Mr. Mukherjee to present the memento to Vishnu sir. So he's online.
Sir. So Vishnu, thank you so much. Thank you.
Thank you.
You should reach to Vishnu.
Okay. Next, we have Dr. Manivannan online. Okay. Actually, Dr. Manivannan has been significantly contributing in the area of tactile internet. He's from IIT Madras. So I would like to ask Professor Lal to present a memento to Dr. Manivannan.
This new way of presenting mementos, this one for Professor Manivannan. Thank you so much.
For Dr. Prasad, I request Professor Lal to present this memento. Okay, Mr. Mukherjee would be presenting this memento to Mr. Prasad, Dr. Prasad.
Dr. Prasad,
Thank you so much.
Thank you. We shall reach this field. Thank you.
Next, Mr. Mukherjee, request you to please present this memento to Dr. Gokhale.
So, Dr. Gokhale, memento for you.
Thank you so much. Thanks everyone for connecting. We can now wind up. All the participants, you can collect your kits and certificates from the registration desk outside and join us all for high tea. Thank you, Mr. Alok.
Thank you, Miji. Have a nice day.
Thank you. Sure, sir.
Somebody put those